And I think that looking out at this room, probably all of us were privileged in a way that today's college students are not. I mean, how many of you actually like the world of the computer? I think many of us did. I think for me, the juice of this discipline is this idea. We're sort of many of us fueled by a motivation that comes from a confidence that comes from the knowledge that the mystery is solvable. We're all kind of like Detective Columbo. Like, we know we're going to get it in the end. And that gives great motivation to probe, the difficult mysteries of our world. We have so much power in computer science and so much leverage on hard problems that, other fields of endeavor don't have. We can rerun, if the mystery is wrapped up in the world of the computer, we can rerun it as many times as we want, knowing we'll get the same outcome. We can inspect any part of the system, because of Turing completeness without altering it. This is a privilege, the biologists don't have. You can't dissect a frog and keep it alive. And the astronomers don't have this privilege either. They see a very interesting supernova. You can't say like, oh, it again, we'll get the telescope pointed at better. They only get a limited number of shots. So we really have a great privilege in the computing arts. And it's a lot of fun to try and, create something from scratch in this world where you have so many kind of bumpers and so much safety. And I don't think that our new entrants are getting the same kind of playfulness and joy. I think if you look at people learning, computing now or engineering, I don't know, how many of you have kids, college-age children? Great. Well, I'm not talking about any of your children, but speaking very generally, I think the young people of today are fueled by a great anxiety about what the future will hold. That probably many of us also feel. The idea that computing is about, what I grew up with in the 80s with like a Mac, the idea that you want to make a thing you can play with it. You do something, the computer does something, and then, the coolest part was to create something that's playful that you can show to someone else. I think we're losing that a little bit. I think it's much more common to kind of either try and live in a test suite, it's like, well, my job is to make these tests green, and there's not a playful thing that I'm creating, or to live in a world where you push a button, then you wait 6 hours or 6 days or 6 weeks, and then eventually you get back some very fuzzy statistical thing that like maybe did it right or maybe didn't do right. This is the less fun part, I think. And so I think it would be really nice to introduce people to this world in a way that emphasizes kind of the playfulness and the interactivity with the real world. And so we have started a new class at Stanford that's hopefully going to be an alternative intro sequence to computer science and electrical engineering that emphasizes this kind of playfulness and joy of being Detective Columbo, of playing with the real world. So the idea is to really connect students with like a live artifact, like the real world. And so, and it's an engineering class. So on the first day, everyone gets one of these toddler xylophones, a smaller one than that, with like 8 notes. And we talk a little bit about, what is this thing? What is sound? It makes these sounds, and like it's a pressure wave. It's a variable air pressure as a function of time. And how do we describe it? There's the frequency. There's the amplitude. The amplitude you could measure like with a barometer. It's really the air pressure going up and down. And now that we can talk about these things, what is the relationship of the frequency between these sort of 8 notes of the xylophone? There's these very beautiful mathematical relationships, like a fifth, bum, bum. That's a 3-to-2 ratio of frequency. And that was discovered in the West by the Pythagoreans. And they were really into this idea of like these rational numbers, like 3-to-2 was like holy for them. And like a fourth, 4-to-3, that's like holy for them. And like they love these rational fractions with small integers. So much that supposedly that they had a guy in their world who proved that the square root of 2 is not one of these. There's no rational fraction for the square root of 2. And that guy, apparently they just drowned him. They're like, this cannot stand. And so that's where our musical skill comes from in the West. But actually, in China, they came up with a very similar musical scale, also thousands of years ago, with a very, very similar intervals. And they had a sort of Confucianism notion of these relationships. So how is it that the ancient Greeks and the ancient Chinese came up with the same? Anyone ever noticed, like, the American national anthem? It's a British drinking song, but it begins da 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 da. The Chinese anthem, it's the same notes. Da 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 da, because of these sort of mathematical relationships that are sort of eternally true across thousands of years and thousands of miles. So these kinds of concepts in the real world, it's fun to talk about. And then how would you bring this information into a computer? If we have a pressure wave and air pressure is a function of time, like how do you talk about that? How do you reason about that? How do you measure it? You might think, well, I have to capture the air pressure at every moment in time. That's going to be an infinite amount of information. But it was discovered pretty recently, like after relativity, after quantum mechanics, they discovered this thing at Bell Labs that no, actually, if you can describe the sound not as an air pressure as a function of time, but if you can describe it in the Fourier basis as a series of these eternal phasors, and we can say it's only a limited band of these phasors that are making the sound, then you can capture it with a finite number of measurements per second and get all of the information. That's like a mind-blowing fact. Okay, so now that we have this information in a computer, how do we know what's happening? How do we know, for example, which note on the glockenspiel is playing? How can we teach a computer to think on our behalf? So it would be fun to write little programs to understand the audio when it's coming in and figure out, what notes of the glockenspiel are playing. So, we can talk about how you do the dot product. You make a sine wave, you do a dot product, and then you can figure out what notes are playing, and then maybe you can come up with a little code to map like the English letters to the notes, and then the midterm exams, like I come and give you okay, so we need some way to teach a computer to think. So we need some kind of language that we can teach new people. It's a very simple and regular language designed by idealistic, mathematically inclined people who get together all the time and very carefully discussed, very carefully, sometimes so carefully that GitHub used to need so many clicks to even read the comment thread about how they made this decision, like many clicks. Very carefully designed, very regular, very simple language with almost no syntax. I think if you're teaching freshmen in C++ or Python or Rust, these are very complicated languages. It doesn't seem like the way you'd want to bring new people into them. In fact, I think if you want to teach new people to program, we should be putting our best foot forward. We should have, this is sort of I don't intend any invidious meaning by this, but it would be nice if the introduction class had what you might call like a first date mentality. Like if you're going on a first date, you probably dress nicer than you normally do. Maybe you put more effort into grooming or shaving, this kind of, you want to put your best foot forward. You want to look like the best version of yourself on the first date. And, maybe hopefully it sticks. Or maybe if your parents are coming over, you're going to clean your house. Maybe it's not normally like that, but you want to put the best version of yourself. And I think we owe it to new people to show them the best version of ourselves. We should show them the version of the world of computing that they are entitled to, even if that's not what the real world is like. I want them to learn a sense of entitlement about what they should have, so that later they can feel the cruel weight of disappointment that the world is not living up to how it ought to be, and then be fueled by that to make it how it ought to be. I think if you just show them mediocrity from the beginning, no one realizes that you can have better. So this is narrowing the scope, I think, of languages that you could really want to teach people for. What should be the language of thought? You might think, well, it should be, C++ or something like that. I don't know. Maybe we don't. Maybe no one thinks that. That's a very complicated, sort of painful language. You might think, oh, Rust, an incredibly sophisticated language, incredibly great tooling. I like Rust, and there's very sophisticated tooling, but you forget one semicolon, and Rust Analyzer will use up all your memory, printing out the error message. It's very easy to OOM kill Rust Analyzer, just like with one forgotten semicolon, especially as there's a lot of macros and that kind of thing. So I don't think Rust is actually the first date we want to go on with new people in the field. I don't think you want a language that crashes, the Rust Analyzer crashes you all the time. So we need to find some language that has robust tooling, very simple syntax, and you can learn it in a day, and you can do anything you want with it. So that leads to a pretty small list of languages. You could think about maybe Scheme or something like that, but what about a language you'd actually want to run in real-time to do real-time audio processing that you actually use in any environment? I think that's WebAssembly. And so I think that is a way that you could teach computer science and electrical engineering to new people. So we have spent the last about a year building a live programming environment for WebAssembly that tries to bring people very gently. And we teach them in the very first day of this class. We say, okay, first we're going to talk about the syntax of this language of thought, this language of computation. Let's see how we're doing on time. And the syntax is very simple. There's going to be a thing called an expression. An expression is a sequence of instructions. An instruction can be a plain instruction, in which case for us it's on one line, or it can be a structured instruction. There's a small list of those. Block that contains an expression, loop that contains an expression, if that can contain one or two expressions. That's the whole syntax. And that's the end of the first day of the class. So day 2, we come and we talk about, okay, so there's going to be some semantics. What do these instructions do? So we give them this environment, and we say, just start writing things, and you'll see. So let's write an instruction. What's your favorite instruction, Ben? I-32, what was that? Add. Okay, great. So I-32 add. So you type this, by the way, this is a live website right now. You can go to codillon.org, you can see it. I-32.add. Why don't we start with a simpler one, and we'll get there. So first, you can see we really try to be forgiving. So there's a sense here where first of all, we really try to honor this distinction between well-formedness of the text format and validity of the abstract syntax, and then the execution time trace. So this is all built on Wasm tools, and Alex very kindly indulged me in making that distinction very precise so that we can have this editor where we make it impossible to make a syntax error. So if I'm in the middle of typing an instruction like I-32, this is not well-formed WebAssembly. So we just have this little musical notes here symbol to say, you're probably still composing that line. You probably just haven't finished composing that line yet. So this is, I can type other things here. If I wanted to type NOP, that's totally fine. But this line is disabled because I'm just still working on it. So we have this notion of disablement of the lines. And if I start a function, I probably was going to finish that anyway. So we'll insert the text for you, func close. If I type open func, we'll insert the close parenthesis. So we try to fix any syntax error. And we basically can do it. Maybe the people here can think of a syntax error we can't fix, but I'll tell you, it's going to be a little bit subtle. And in any event, if we really can't fix your syntax error, then we just forbid the keystroke. So it is not possible to make a syntax error, but 99% of the time we do it with some very nice UI, and the remaining 1% of the time we just bounce. We say, no, you can't do that keystroke because that would have made a syntax error. So I open this func. I haven't closed it, but if I want to close it, I just close it, and then boom, it closes. So I have a beautiful function now. And then let's do a NOP. So I'm still composing it, N-O-P. Now I have a NOP. That seems very nice. Let's do maybe a constant. So we have a little symbology here. So we'll do I32.const. What's your favorite number, Ben? 42. So we expected an I32. So 42. Okay, so now we have a little visual symbology here where there is the I32. It's right here. There's the operand. It has a shape. Maybe if I don't execute this, it has a shape just for the type, which is this little blue square. And we can make an I32 looks like that. An F32 looks like this. An F64 looks like this. And an I64 looks like this. So we have this little symbology. But there's also executing live. So whatever thing you make here, it's actually the number. It's actually the operand. We're I32, and we can go and make this bigger and bigger and bigger until eventually you can't do it anymore. And now this is malformed again. We disable the line. Okay, so we got a 42. I don't know, what's another number? 34. Okay, do an I64.const 34. So we have these things, and then let's, you said you wanted to add them. So let's do an I32.add. Oh no. So every operator is associated with a function type. And we display these function types as a sort of Jensen fraction. This is abusing the notation a little bit, but Conrad's not paying attention, so I think it's okay. The notation here, there's like a numerator of this Jensen fraction, or that says if the suffix of the stack contained an I32, then after this, the same suffix will contain an I32. So we display the function type in this sort of, implication type language. Now this is not working here. Why not? What's the invalidity? We have this nice little X. The types are wrong. So this big thing can't fit in this little box. And if we made it an I64.add, now this little thing doesn't fit in there. But if we make these both I32s, now it works. And we get the sum. So again, it's executing live. Oh yeah, we have this autocomplete. So this is the symbology. Yes, Thomas. Well, I'm glad you would ask. So you can try this. This website is live. I'm just using the public version of the website, but let's do it. So in unreachable, can I do return first? Okay, so let's do return. So if I do return, here's what happens. So first of all, these get eaten up by the return instruction, even though they're not the return type of the function. They just get eaten up, popped in, and not used. And then the add is now here in a polymorphic stack. So we can see it's getting something because it's shaded here. If I had an add here, let's do it at the top. You can see, these sockets are empty. But this add, the sockets are full, but they're full with a polymorphic type. So you got some more stumpers? We spent a year on this. I'd be very happy to. Okay. Now, sorry? Yeah, well, that's the sort of polymorphic mystery type. Now, you can also get the polymorphic mystery type and not be satisfied. Like if I just do a drop here, we get that. But if I do return in the drop, now the drop is satisfied, but we don't know with what type. Now, if you want an actual unreachable, so I'll show you how we do runtime traps. So if I do i32.const6, i32.const0, i32.div, now we get a integer divide by 0. And this is just coming from the browser. And to be clear, we can execute this step by step. So we can say, we're about to do the 6, there's the 6, we're about to do the 0, there's the 0, we're about to do that divide, boom, now we get the crash. So you can go back and forth. All right. Any other cases you want to see, or you want to do a little programming demo? Let me show you, like, the blocks might be fun. So if I type block, the instruction, I quibbled about this the other day, but, the instruction is block end or if end or if else end. Just block by itself is just an operator. It's not an instruction, but we do try to be nice. So if you haven't done it, we just have this sort of disablement here. We just show you, hey, we would really like you to clean that up. If we do an if, then you get this little if block here. And of course, the type of the if is it has a predicate. So, we'll give it some sort of predicate. And the if can also take, params if you want, and then this just become other params. If we add in an else, then, these params appear in both branches of it. You can also have like result types, I don't know, i64. So then you end up like with this. And then you do have to satisfy them in both places. Oh, by the way, if this is not an if, then else is not valid here. So we just disable that. That's a syntax error. So we go back to the if, what could I do here? I can draw this thing, and then I'll make an i64.const8. So, but we're still bad here. What happens if the else branch is not here? So this is actually annoying because the validity error is in a branch that's not really taken here. This sort of omitted else is like a shortcut. So we try and tell the student, like, hey, it's in the implicit else branch that we have this type mismatch. So we're trying to be kind of friendly here. I can show you loops, which is maybe a little fun. So if we do a loop, how are we doing on time? It's 10 minutes. Okay, so let's do a loop. So here we have this loop, and we can do, i32.const5 and i32.const6 or something like that. Or, let's do some locals. I don't know, local x i32, and then let's local.get x. I don't know, let's add 1 to it. i32.const1, i32.add, and let's just local.set x. So what's the problem here? This is only running for 7 steps, right? If we go back, we can see, we're about to do the loop, 0. So what classic mistake do we make here? It's not looping because there's no branch or break instruction. I read, how many GitHub comments I had to read to figure out if it's branch or break, and I had to keep expanding, and the answer is you never made a decision. Anyway, so the BR instruction, either branch or break. So, if you don't actually branch to the label, it doesn't do it. So let's give this loop a name like my loop or something like that. And we can do branch my loop. And only now that it was taken, we put this little loopy-doop on the thing to show you that it actually got taken. So if you don't see that, then it wasn't really a loop. And, you can see here at the beginning, we're going through and we finally get to the branch. And I don't know, why didn't it put it on? I just added this during lunch instead of talking to all of you, and I'm it got put on at some point. All right, we'll figure that out. Okay, anyway, so, we can do return call if you want to see that. I don't know. Oh, we can do recursion. That's kind of fun. So I do call 0. Oh, so now I have an infinite loop here, but we just cut it off after 100,000 steps. Now, if you want to see stack exhaustion, I have to go to Chrome because for some reason, Firefox has a more liberal threshold. But in Chrome, if I do call 0, then after 41,000 things, I get this range error, maximum call stack exceeded. I have to tell you, it is not easy to recover from that. That was actually difficult, but you can actually recover from that if you, don't. Anyway, it was annoying. Yes?
I have one more question about the visualizing of typing.
Yeah, please.
Do unreachable and then select.
Oh, yeah. Run reachable and then select.
Oh, lovely. And it is correctly invalid. That's nice.
Thank you. Yeah, I mean, we worked at this. Okay, so let's do a little programming demo. So if you want to be understanding what's in the toddler glockenspiel, you probably need to make some sine waves to dot product with it. So let's make some sine waves. So first, we're going to have to probably import some functions. So let's import, or we'll do func. I don't even know how okay, so func, and let's import something called draw, point, And I'm supposed to have params f64, f64. So if it's unlinkable, again, we just don't let you do it. So let's make it param f64, f64. And let's call that like draw. And then let's do another function, like, I don't know, just for fun, radius, import draw, set radius, param. I think it's going to be f32, I'm guessing. No, it wasn't, f64. And then let's, you know, to be vain, let's do some colors, import draw, set color. And that's going to be param I32, I32, I32. Okay, great. So if we're going to draw this thing, first we should probably do some sort of setup function. So let's define that setup function. So you can program very incrementally this way. Like I called it, it doesn't exist yet. That's all right. So let's make the setup function, and let's I don't know. Let's have a nice color. What color do you like? Periwinkle. Great. You got some RGBs for that? It's like a little pink, right? So let's try like 200. I don't know, 50. We'll put some blue in it. Maybe 40, 70. Call set color, or I think it was just called color. There we go. Well, too late for that. Oh, are you serious? Okay, give it to me again. Great. What is it? CC. FF. Great. Okay. You see how the line, you see it's just sort of impaired if it doesn't really fit, and then FF. Great. Okay, so that's apparently periwinkle. Let's get some nice radius here. Maybe, I don't know, 8. Okay, great. So it didn't take it. What did I do wrong? Oh, because it's an F64. You can see because it's this big thing. So it should have been an F64. Great. Okay, so now we got something. And then, I don't know, let's draw a point once. So we'll call that. So let's figure out. So we should probably keep track of where the point's going to be. Func make point. So probably I'll just make like a global here. Where do you want? Let's do it like over here to start. So there's the global, you can like see it manifest, and let's make another global, f64.const0. So we'll just do global.get x. Oh yeah, we should give these names. Why is there no global.t? All right, call draw. Okay, so there's our point. I would call that periwinkle, Nick. Okay, so there we have our periwinkle point. So now we gotta like move this thing around, right? So let's make some sort of loop here, each point, and we'll just go back to it. So now we're definitely looping, but we're like infinite looping. So probably we should only loop like a little bit. So call should we continue, something like that. We'll make this a BR if. So now we owe it an I32, should we continue? So let's see. So func should we continue? Let's make a global for the number of iters. I would pick a random number like that, and I think we'll just do like global.get iters. Oh, it should probably be mutable. And let's subtract 1 from it, and then set that back to iters, and then we'll just get iters, and we owe this. Okay, great. So now we're only looping a finite number of times because we're just, you can see what's happening to this global. As I drag through here, you can see that number just gets smaller and smaller and smaller. So you can really kind of inspect any part of this. I know people talk about debugging. I think this is better than even like Scheme or these REPL-based languages, because every part of the state is visible, and you can just see what it is at any point, the globals, locals. You might notice here, there's no operand stack. As the people in this room probably know, like you don't need an operand stack at runtime in WebAssembly. That's, can be purely a validation time concept. So here we have these operands that are, created at one point and then consumed exactly once, and you just show them with this single edge, and that's good enough. You don't need an operand stack. Okay, so great. So now we have this finite loop. So now all we got to do is somehow change the point. All right, so how are we going to vary this point to make a circle? We should probably have some sort of epsilon, something like that. And then what are we going to do? So we're out here with like a big X. I guess we can move it in a little bit. So we started at 0.8. We could make it like 0.5. Moves right away. So what are we going to do? Let's call this the right edge. So probably we should be moving Y positively. So let's see. If we have a big X, it seems like we want to move Y positively. So let's see. Whatever X is, let's multiply that by epsilon. So we have some product here, and when X is big, that'll be big. Let's just add that to Y. So whatever is Y, let's just add it and just set that back to Y. boom, we have a line. Because you can see what's happening here. We're just, as it executes, we just draw that line up and up and up and up and up. And you can see the arrow going crazy. And we can follow it around like this. But basically, as it's going up, it just goes up and up. Okay, so great. So we're headed in the right direction. So I guess we just got to steer X similarly. So we can get this. And we'll just flip these variables around. So instead of it'll be X, Y, set that back to X. Uh-oh. What's happening? We're curling the wrong way. So what do we need to do differently? When X is big, we need Y to change positively, but when Y is big, we need X to change negatively. So we'll just make this a sub, and then that's pretty good. So we had 314 iterations of 0.01. If we make this 0.02, we get a perfect circle. From that, you can make a sine wave. And what's funny is we're kind of doing the wrong thing here, right? Like we're changing Y, and then we're using that new version of Y to change X. This feels wrong, right? Like we should probably change them atomically. So we can just move this instruction down here, and that feels mathematically better, except, uh-oh, doesn't match up anymore. And if we make our radius smaller, let's make it just 1, and we do some more iterations, you can see this does not work. The mathematically pure thing does not work. Does anyone know why? This is actually a very deep thing that would be like in a graduate physics class. If you do it this way, this is called the forward Euler integration. It's not energy preserving. This like particle gains energy every time. And you have to do what's called the symplectic method, which was, discovered by Marvin Minsky in the 1970s, the so-called Minsky circle algorithm. If you do that, then even if you run a bajillion iterations, it's perfect. It overwrites itself. So that was a discovery in 1972, the Minsky circle algorithm. And now, the freshmen are kind of discovering it by trial and error. I had some students, she missed basically the first third of the class, and I was like, this is hopeless. You're going to have to learn WebAssembly, xylophones, Chinese history, sine waves. She's like, well, just tell me what you have to do. I was like, you have to draw a circle. And she fought with it, and she got it close, so that she kept playing, and then she got the freaking circle. I was very surprised and impressed. Somehow this kind of playful interface really helps. So from here, they make a sine wave, and then they convolve with, they dot product with xylophone, etc. So stepping back for a second, I think WebAssembly is a good language to introduce people to computer science because it is very simple and regular, and you can learn the syntax in, very quickly, and the rules for execution are not so complicated, at least the sort of Wasm 1.0. The rules for validity are not so complicated. So I think this is a good way to introduce people, and then, we can show them, hey, this is what a compiler produces. Everyone is ultimately using this, probably not directly, but through a compiler. And I think we can do some real-time playful projects with it, like understand what a xylophone is doing. That would be difficult to do in Python or the kinds of platforms that students are using to learn computer science. I want to pause here for questions, and then I'll give my peroration if I have one.
Questions for Keith?
The interface here is obviously intentionally very clean, right? But I wonder about discoverability. Like, how does the student know that some new instruction even exists? Are they told about it in class and then they use it? Can you press question mark and get like a whole list of instructions? How does it work?
Yeah, it's a good question. So right now what we have is autocomplete. So if I'm interested in doing something with an I-32, I can't type I-32, and then you see at the bottom here, I have all these options. And this gets you pretty far. I sometimes say like, well, you're doing something with an I-32, why don't you see what's available? And they say, oh, maybe I want this thing, etc. So that's what we have. So the naming of the instructions is very nice. It's nice that it's not the pre-MVP instructions where they were kind of a little more free-form. So, you could imagine it would be possible to do a search by type, what would be valid exactly here. I don't know how often that would be exactly surfacing the right thing that they're looking for. We could probably have an LLM be like, Clippy, like, did you want the whatever instruction? That's kind of the best I have, is like autocomplete and look around. So we tell them there's 4 primitive value types, and we kind of let them go from there.
Can I just say, how dare you, sir? Proportional font.
Oh, well, so this font has a whole history. Oh, I didn't show you the comments, but this is a comment. So these are both versions of Computer Modern that were, created at Stanford. So this is the, yeah, you don't like, I don't I like it.
I mean, I learned on DOS. I mean, come on.
Yeah, I just want to say your intro about, kind of the joy of computing and like discovering them. And that question reminded me that I learned so much about computers by typing question mark or help or something like that and just getting a huge menu of possibilities. So that's a cool thing. But my actual question was, how do the students like this? What are their reactions? Do they say, wow, this is so fun? Or do they say, what is this weird language? It's so odd, it's so different from what I've learned before or whatever?
It's a good question. The first crop, so I taught this once this past spring, and I had 10 students who self-selected into it based on my description. And the description was trying to be clear that they would need a sense of adventure to do this. So they loved it. But, that probably won't generalize if it's 100 students. I think not every student is able to teach themselves, sort of constructively by just sort of self-guided play. And so this is, probably many students would need a more regular curriculum. And I don't know if you've seen Hazel or these other kinds of attempts by PL people to do education. Hazel's by Cyrus Omar and his group at Michigan. There's some theories that like, okay, maybe you have a fun language, but also like you have to write some tests, or, we've written some tests and you have to pass the tests. There's ways to make this more like homework and less fun, which it's not my thing, but I think some students probably do need that to learn.
Is this for majors or non-majors?
I need to figure out how to phrase it to attract the right group of students. It's for freshmen, so they're not majoring in computer science yet. And part of the benefits of choosing WebAssembly is you don't get some kid who's like, oh, my dad taught me this language when I was 6. That's because all of you are not, having enough children and teaching them WebAssembly when they're 6. So, it is a bit of an equalizer, which is also a benefit you get from Scheme or something like that. So the whole class kind of has a little bit of a communal, like we're all in this crazy class together, like we got to figure out this unknown world together feeling. So that's helpful. But I need to find a way to describe the kind of sense of adventure that we're looking for.
Some people might go on and major in computer science.
I think so, yeah.
Cool, thank you.
I have a question.
You can let Francisco first. Francisco first.
What happens when you want to introduce words to your students?
I know you don't mean a 16-bit region of memory.
No,
what do you
I
mean by
mean words like hello world,
Oh, yeah. Well, I think there's a few ways we can do it. We do have support for, memory here, and we're working on sort of memory visualization. So, I can make a memory. Actually, so one thing you might find interesting is, we emulate custom page sizes. So the browsers, it would be great if the browser supported this, but we support custom page sizes, and we emulate that for for our students because here, let's just do a memory 1, page size 1. So I think this is a 1 byte memory. We could make a memory 4. So if I do func, if I do, f32.load, so what do I need? i32.count 0. So this is fine, and then this traps. So the browser, I didn't tell you about how this works, but so we're taking the WebAssembly that the students give us, and then we're instrumenting every line of it to be able to capture the operands. And this is not super easy because some operands have multi-value returns. And so there's no inline way in WebAssembly to capture these multi-value returns and then put them back where you found them, because there's no like stack exchange, this kind of thing. So we have to.
This wasn't what I meant.
Oh, okay. Sorry.
So the next thing after xylophone is reading a dictionary. So, or doing something with words.
Yeah, I think that's possible. I think, honestly, we would like to have them learn a little interpreter or design an interpreter for a language, and then, write things against their interpreter, that kind of thing. But yes, I think you're right. So whether we do that with linear memory or with heap types, I don't think we've decided. Is that what you're getting at? Should we be doing heap types versus linear memory for these concepts?
Well, I think WebAssembly is not a good starting base for anything to do with strings and words. So
Well, you may be
if you do
right,
either one,
in
if you
which
do the
case-
structures or if you do that, then you're really sort of throwing people in the deep end for anything like this.
Well, you think scheme would be better?
Probably, but I'm not advocating scheme.
I mean, the truth is that when we design the next assignment, we will do it to be appropriate for the scaffolding that we're giving the students. And it may be that not every part of computer science, I mean, it's definitely true, not every part of computer science is going to be pleasant to do in raw WebAssembly. And so we probably won't have them do that if we can't find a way to make it a good learning experience. We could teach them, hey, WebAssembly is really mostly a target for compilers. There are things called compilers. And so, there are higher level languages where whatever concept we're talking about would be more naturally or pleasantly expressed. And here's how that might be lowered into or compiled into WebAssembly. I think those are valuable things for students to understand. And so, the kinds of assignments you're talking about, we might not do if we can't find a way to do it pleasantly. I guess I was optimistic that we could do, an interpreter quasi as pleasantly as you would do it in Scheme or Racket, we could do in WebAssembly with heap types, but maybe not. And I think we'll have to try it to know for sure. You may be right. I'm not going to try and defend WebAssembly against you, Francis. Like, if you think it's bad, like I'll. I respect it.
It's the educational value of making WebAssembly the first language that someone's. You said at the beginning that you wanted this to be like the first date.
Yeah, I do think this is better than you will get from any other programming environment. Maybe this is what people keep raving about, but you did not have this on the Lisp machine. You don't have this in Scheme or Racket. You don't have this. I mean, even in a REPL-based language, the REPL, the environment is a hidden state. You have to go probe it by evaluating expressions, and here the entire state is visible, and I think that's really nice.
I agree with that.
This is sort of like Scratch, with typing, typing on the keyboard, not like smart people, but just like it's like Scratch with a source language.
Okay, I'll try and be very quick. How well are you able to protect the students, if this is their beautiful first impression of computer science, from accidentally also having like a Python course in the same semester and also getting into to coding that way?
Well, so the students I had the first time, many of them had already taken, just because of who I got, a Python-based class and then a C++-based class. And neither of those, I would say, super prepared them for this class. So I don't know that it would be...
It's the opposite. I would worry it would ruin them for this class.
No, they seem to like it. Maybe because I brought them chocolate and I took them to the Computer History Museum. I don't know, but they were a good bunch. I don't think if they were taking a Python class, that would be a class with 700 people in it, in which 80 of them are there in the lecture hall. It would be a very different kind of class. It would not be a class about playfulness and interactivity and kind of learning by mucking around in the mud. So I don't know if it would be a conflicting cognitive goal. I mean, those classes, by the way, now there's like interact with an LLM to do things. I mean, those classes have a broader agenda. Yeah.
What happens if the students just playing around and they type like V128 dot?
I think currently we have just forbidden that. V128 dot, yeah, we just don't do it. Sorry. Yeah, so this is a case, for example, we're just like, no, we don't like this keystroke. We just won't even, we won't let you type it.
All right, I think we have to move on. Thanks.
All right, thank you very much.